Good morning, everyone. Thank you for joining us today for IBTTA's Emerging Technology Committees and AI Strike Teams webinar session. We're excited to have you with us as we explore one of the most transformative topics in our industry today, using artificial intelligence technologies to improve roadway safety and operational efficiencies. My name is Richard Jaramillo, and I am the Chief Operating Officer with the Maryland Transportation Authority, co-chairing one of the 4 working groups of the AI Strike Team, along with Marge Rangel. Marge, you want to introduce yourself, please?
Thank you, Richard. I'm Marge Rangel. I work with TransCore and I'm part of the Florida team project. I oversee the toll system implementation for the Florida Turnpike and the Florida Department of Transportation. And it has been a pleasure co-chairing this committee with you, Richard.
Thank you, Marge. I appreciate that. It's been a pleasure as well. This session is part of our ongoing commitment to advancing innovation within the tolling and transportation sectors. Today, we'll be taking a deep dive into the practical applications of AI, from predictive analytics and intelligent traffic management to automation and real-time decision-making tools that are shaping the future of roadway operations. We are joined today by a diverse group of experts and thoughtful leaders who are pioneering the integration of AI across transportation systems. Throughout this session, we will hear insights on how AI is being implemented and utilized, enhancing safety, improving performance and efficiency, delivering better outcomes, and most importantly, providing safety for agency and traveling public alike. Before we begin, I'd like to thank members of the IBTTA and IBTTA's Emerging Technology Committees, AI Strike Team, for their dedication and collaboration in organizing today's program. Your leadership continues to drive forward-thinking dialogue and innovation within IBTTA and the broader transportation community. Please join me in thanking the IBTTA Board of Directors, Executive Committee, and staff for their support in providing this informational platform. I want to also thank George and Raphael for their leadership with the AI Strike Team. Growing from the larger framework of IBTTA's Emerging Technology Committee, the AI Strike Team has established with a core mission for fostering synergies, innovation, and practical applications of AI concepts within the transportation and tolling domain. Our strategy is to harness the collective expertise of public and private sector professionals, catalyzing the exploration and implementation of AI-driven solutions for the betterment of our industry and its diverse stakeholders, with a primary focus of safety to the driving public. Our objectives are twofold. First, to facilitate robust collaboration, research, and ideation, nurturing fertile grounds for transformative ideas to flourish. Second, we are committed to empowering industry leaders by disseminating knowledge and resources, while actively addressing any barriers hindering the widespread adoption of AI technologies. Together, we strive to pave the way toward a more efficient, responsive, sustainable, and safe transportation ecosystem. Let us begin with our session today. Joining Marge and I are Ferzan Ahmed, Road Safety Steering Committee and Executive Director of Ohio Turnpike and Infrastructure Commission, and Mark Franz, Lead Transportation Analyst and lead of the Data Science Team at the Center for Advanced Transportation Technology Laboratory, or CAT Lab, at the University of Maryland. Our first guest, Ferzan Ahmed, is well known to all of IBTTA. And for anyone looking for Ferzan's full bio, please feel free to visit the IBTTA website. Ferzan, welcome, and thank you for joining us today. Appreciate you being here, sir.
Richard, it's my pleasure. And before we start, I want to thank you and Marge for the leadership role that you have taken in advancing this work. You both have full-time jobs and busy jobs, and this is much appreciated. You're doing this for the industry.
Thank you very much, sir.
Thank you, Ferzan, and thank you, Richard, for that introduction. Let's begin. Ferzan, can you begin by telling us about the Be Safe Together campaign and why it is important?
Everything we do, we are in the transportation and infrastructure business. And what does that mean? That means we are in the business of moving people. We gotta, for us to really make an impact in the industry when it comes to safety, we have bridges, we have roads, we have infrastructure, but we have to understand what is all this for? And ultimately, it's all for moving people. And when we put our focus on the people aspect of things, then we all come to the same realization that the core business of everything that we do, whether you're in the private sector, in the public sector, large agencies or small agencies, rural agencies like the Ohio Turnpike, which is a rural highway, or urban agencies such as we see in some cities, we all have the same mission, and that's to move people as safely as possible. And the worst thing that can happen when we are working is when there's a crash and somebody's seriously injured or when somebody dies. The bottom line is when somebody's seriously injured or when somebody dies, it is an entire group of people who are affected. It's families who are affected. It is a community that is affected. And these effects can last a lifetime. Our vision is vision zero, which means zero deaths on the highways. Now, is that possible? Well, I'm not a statistician, so I'm not gonna say whether it's possible or not. Here's what I'm gonna say. Let's think about the things that really matter to us deep down inside as human beings. Things that were taught to us by our parents, grandparents, and anyone else who was important in our life. Never lie. Always be good. Always tell the truth. Nobody ever said, lie just a little bit or tell the truth a little bit more. It's always never and always when it comes to things that are serious. When it comes to traffic safety, it's as serious as that. Our goal is target zero. So when our goal is target zero, having this campaign for all of us together who are in the industry, not just in the United States of America, but in the entire globe, working with other entities such as ASICAP and the IRF in Europe, and working with our private sector and public sector partners last year under the leadership of our immediate past president and last year's president, Bill Helkias, we started the Be Safe Together campaign because it is about us working together to keep everyone safe. And that is why that Be Safe Together campaign is so important in what we do in our agencies and in our work.
Very good. Thank you, sir. So we have another question for you. We often talk about technology and safety, but fail to remember the human side of the conversation. From your perspective, who stands to benefit most from AI and ML application in roadway safety? And what are some examples of that impact?
That's a great question, Richard. I think we all benefit. I think that, when we think in terms of the human factor on the road, well, who is on the road? Drivers, passengers, people who are working, first responders, people who are responding to emergencies. Everyone who's there will benefit from all the technology that we can introduce to keep us safe. Now, talking about the use of technology, well, first and foremost, we use it to monitor, what's going on out there. I like to call that an inventory. Let's take an inventory of the existing conditions. So the inventory of the existing conditions will tell us what we need to prepare for. Now, when we introduce AI and today's technology into that, well, now we're getting into the predictive stuff. Now we're getting on stuff that's based on patterns. And one example I'll give you is there's an area on the Ohio Turnpike. Many of you must have heard of Cedar Point. It's one of America's biggest theme parks. Close to Cedar Point, there's an area that is given to blizzard conditions. And two of the worst crashes we have had in our almost 70-year history happened in a 10-mile segment of roadway. So what is going on? Can we predict, can we predict that there's going to be a crash over there? What I'd say to that is we can use all the AI and all the technologies that we have available, look at all the weather patterns, look at all the traffic patterns, and look at the past history, and then come up with something that gives us and our maintenance people a little bit more idea of what to plan for as we get into inclement weather towards the end of the year. And that includes our maintenance people, that includes the highway patrol that enforces, as well as the first responders. So everyone benefits from the use of that technology.
Very good. Thank you, sir. Appreciate that.
Thank you, Ferzan. Talking about technology, how does technology help improve communication between the partners and enforcement? And do you believe that technology makes us safer?
And I'll give you some examples. I think it's better to give a real life example to demonstrate how it makes it safer. Back in 2022 in December, there was a horrible crash, and it was in a blizzard condition, and it was far away from the building, and it was at a time when no one was working, and we had to rely on people trying to call each other. There's a lot of turmoil in terms of noise, in terms of the storm, in terms of the fact that first responders are trying to get in there, and the communication was based on me calling somebody on the cell phone and then hoping that they'll hear the cell phone, and then them trying to figure out what's going on over there. Unfortunately, in the middle of a blizzard, the cameras are not going to work. So what we have to look at is the worst case scenario. What is the worst case scenario? And worst case scenario means when you don't know what's going on out there, perhaps because of weather conditions or any other influence, something else that throws a wrench into normal operations. And then see what technology is out there that can help us communicate better so that we can inform which way the first responders should be going. Should they be coming eastbound or should they be going westbound? These are very minor details that I'm talking about, but these details can save someone's life. When somebody's hanging on with a thread, getting a first responder to that point in the quickest way possible, and then getting them out of there in the quickest way possible is the key to saving someone's life. And I think that the more technology we have out there that tells us what's going on and what we can do, the better it's going to be. And this is all communication, because it's not one person that's doing anything. It's a group of people. You've got maintenance people, you've got law enforcement, you've got first responders, and then you've got the people themselves who are there. So having the best way for us to communicate with each other is going to directly go towards saving people's lives.
Very good. So Ferzan, IBTTA President James Hoffman, during a previous meeting, had asked us, how do we solve today's problems with regards to AI technology and so forth? So we ask you, what do you think are the key steps we need to take to solve today's safety challenges and get closer to the Vision Zero?
Thank you. There are a lot of resources available in IBTTA. James is very passionate about seeing that we get this done this year. Look at all the wealth of knowledge and information that we have, not just in our country, but we have so many other examples from other countries that we can tap into. I think that when you are looking at solving a problem, you have to first define what that problem is, and then make sure that everybody understands that this is a problem, and then we have to define that solution. So the problem as it exists today, today's problem is that we do have a lot of road deaths and a lot of road traffic crashes and a lot of safety issues out there. Some of them cannot be helped, but a lot of them are due to driver behavior, people not paying attention, people being distracted, people getting behind the wheel when they should not be getting behind the wheel. So that is today's problem, Richard. That is the problem that we need to solve. And one of the ways that we can solve that is by looking at our public sector partners as well as our private sector partners to look at actual case studies. You know, in your agency, you're doing a lot of different things. My agency, we're doing a lot of different things, but we have so many other agencies too. So let's start pinpointing what we have done and what good results that have come out of those efforts, and share those results with each other. That's one way of doing it. Our private sector partners are going to play a key role here because they are the ones with the innovation. They are the ones who are creating new programs and new solutions that we can incorporate. That is the approach we have to use. Get that inventory first, make sure everybody understands what that issue is, and then let's share that knowledge with each other, and let's bring in the innovation of the private sector.
Very good. Thank you, sir.
Thank you. One more question from me. We hear a lot about the cost of taking no actions. How do we balance inside the agencies? How do we balance the cost of remediations, and how recent technologies can help?
You know, most toll agencies are public agencies, government agencies. And I've been in the public sector for more than 3 decades. And sometimes there's a stigma that things don't move in the public sector. You know, I'd like to dispute that. I don't think that's true. I think that we all care to get the same results. I think that where sometimes in the public sector your hands get tied is because we are the public sector, there are certain procedures and there are certain hoops that we have to go through. So, for example, if Marge, if a company out there has a brand new solution that has not been implemented, as a public sector executive, it's harder for me to say yes, I'm going to try it versus if I were the head of an agency that's in the private sector. So, what would work in a scenario like that is show me how this helps, show me how this tackles, as Richard called it, today's issue, how it tackles today's issue, how it solves a key problem. Show me exactly how we get to that solution. And then what happens if we don't implement? I think you said that, the cost of not doing something. So what happens if we don't implement that? And I think that if we have an actual pathway that shows how we can get it implemented and what we're missing out on, that kind of an approach makes it easier for a public sector entity to adopt a new technology. It's not that we don't want to adopt new technologies. It's just that because we are a public agency, because we are government, there are procedures and processes that we have to go through to adopt those technologies. And I think the more dialogue we have with the private sector to explain to you what those procedures are, and then the private sector partners can present it that way to us, and I think that will close that gap.
Thank you, Ferzan.
From a policy perspective, what challenges or opportunities do you think agencies face when looking to implement AI and ML?
So, anytime you have something new, the biggest challenge is going to be there is no policy on how to implement that new aspect of technology. In my state, in the state of Ohio, we have an IT governance board. And the IT governance board was created by our governor to make sure that whatever we are implementing achieves something that is part of his vision, and that it is done in a way that it is sustainable based on the IT systems that we use in the state of Ohio. So a lot of people look at that and they will say, "Oh my God, we can't do anything." So no, that's not what the governance board means. That means let's look at what the governance board has, let's see what the steps are, and let's communicate those steps, and then take that. So the policy would be, let's, adopting something new, adopting a new technology that benefits something should be part of that policy. And if there are states or agencies or entities out there that don't have one, then I would encourage them to have that policy because it really helps. And the best way to grab that, put that policy in there is to first and foremost identify why. Why do we have a policy? So if If give you an example, if I wanted to implement some sort of an AI technology for wrong way driving, well, why? Well, why is very simple. In this particular segment of the road, there have been wrong way drivers. So I would like to implement a policy to adopt new technology that helps us detect and prevent wrong way driving. So having that policy is very important because then you can take a step-by-step approach towards implementing new technology.
Very good. Very good. Thank you. Thank you very much, Ferzan. I want to again thank you for your time, your vision, and your leadership, sir, in all you do with IBTTA and Ohio Turnpike. Very much appreciated, and thank you so much for your time today.
I appreciate that very much. Thank you so much for including me. It is my pleasure. It's great to see you guys again.
Thank you. Our next guest is Mark Franz. Mark Franz earned his BA in physics and BS in astronomy from the University of Florida, his MSCE from West Virginia University, and his PhD in civil and environmental engineering from the University of Maryland, with an emphasis on transportation engineering. Currently, Mark is the lead transportation analyst and lead of the data science team at the Center for the Advanced Transportation Technology Laboratory, or the CAT Lab, at the University of Maryland, where he is developing and improving online transportation analysis tools and visualizations for public and private sector clients. Mark, welcome, and thank you for joining us today.
Thanks for the introduction, Richard, and for the opportunity to present our research. I'll go ahead and share my screen and get started on our presentation.
Thank you, sir.
Can you guys see that okay?
Yes, sir.
Okay, great. So again, thanks for the opportunity and the interest in our research. Today's presentation will focus on our work on a recently completed project where we developed a queue monitoring and prediction tool that's online. It kind of automates the process of bringing in the data and then displaying that information on a user-friendly interface, which I have some screenshots of in my presentation. I'll mention here, given the time constraints, this is kind of an overview of the project. So I'll talk a little bit about the motivation, the data that we have used, the methodology, and then show you some screenshots of the tool that is up and running and currently being used by MDTA. So as I mentioned in my presentation today, I'll go over the background and motivation, the model development, and the assessment, which also includes a brief description of the data that's being used. And then I'll get into the interface designs and functionality showing how the tool works and is being used by MDTA. And then I'll wrap up with the conclusions and next steps. So for motivation and background, for those who aren't familiar, Maryland's Bay Bridge, located here, is a critical piece of transportation system infrastructure, not only in the state of Maryland, but also for the East Coast. It's the only bridge that goes over the Chesapeake Bay. So when you think about the impact that would have if there was a major incident or closure of the Bay Bridge, and you can go to Google Maps, when you're able to use the Bay Bridge, you can usually get to Ocean City, Maryland from, just outside the DC area in about 2 hours and 14 minutes. If the bridge goes down, you have to go around the entire Chesapeake and back down the eastern shore of Maryland to get to Ocean City, and it almost doubles the travel time. So it's a critical piece of infrastructure and one that MDTA is constantly monitoring to make sure they're performing as well as they can in terms of providing a safe and reliable means of getting over the Chesapeake Bay. So our motivation was after we had some initial discussions with MDTA, it became apparent that their current methodology to operate and manage the bridge was more of an ad hoc process. So they had data that they're using, even things like Google Maps, other data that's being collected by MDTA and Maryland DOT. But all these data sources and visualizations were spread out across different applications. So it was kind of difficult to link them all together to use that for real-time decision support. We also learned that they do try to estimate what conditions are going to be in the near future so that they can make adjustments to the closure of lanes or reversing some of the lanes at the bridge so it can better serve the east or westbound movement. But those estimations were generally coming from the operator's experience. They used the data they had in front of them, but they didn't put it into like a predictive statistical model. It was based on their judgment. So we saw this as an opportunity for the CAT Lab to develop an online tool that would bring all of the data that they're currently using into one place, and then also provide some intuitive visualizations of that data so that the decisions that are being made can be easily visualized and communicated to a wide audience, whether it's people working for MBTA or to the general public, about explaining their decisions on how they manage the bridge itself. So what we did is we developed this online tool where all the data comes in, and we have two general applications that are currently being supported by the tool. The first one is just real-time conditions. So we have real-time data feeds with sensors, vehicle probe data, weather data that are coming in. So at any time we know what the speeds and the potential cues are going on. But perhaps just as important to that is the predictive conditions. And so we developed a methodology that would help MBTA use the data that they're already collecting as inputs into the model to predict what the conditions would be at some point in the future. The current tool is able to predict out to 30 minutes into the future. We're going to have future enhancements to that to expand the prediction horizon, which I'll talk about in the next step section of this presentation. But in any case, we feel that this tool is enabling MBTA to be more proactive about making interventions to reverse lanes and open and close lanes, which has an impact on safety as well as the mobility at the bridge itself. So it's lots of benefits to the general traveling public on Maryland's transportation systems. So I'll mention here too that while this presentation will walk through the use case for what we developed for the Maryland Bay Bridge, we built the system so that it's transferable. So we could do this pretty much anywhere, a bridge, a tunnel, even an interchange if that was an area of interest. The same methodology and general visualizations can be used in those scenarios as well. So I'll talk briefly about the initial model development assessment. And I'll just mention here, I'm going to keep this very high level, but if there are viewers of this webinar that want to learn more about the details, we have a reference at the end of the presentation for a TRB paper that we published. And my colleagues and I at CAT Lab are also available to hop on a call, give you a live demo of the tool and talk about the details. In any case, the current model is really just using, for the prediction part, is mostly using vehicle probe data. For those who aren't familiar with that, this is data that comes from connected vehicles, cell phone devices, vehicle telematics, and we're getting pings, and we're able to determine what the travel time and speeds are on predefined road segments that are called traffic message channels, and we otherwise in the industry call it TMCs. So what we use is we use the data that we get from these vehicle probe data providers, and we're not only looking at the real-time conditions, but also the previous 6 time-minute intervals so that we can see if conditions are improving or getting worse or kind of staying the same. With this data also comes some metadata that gives us information on what the free flow speed is on a given road segment, which is generally measured during the overnight hours when there's not congestion. So we know what the sort of the free flow, or sometimes it's called reference speed. And we also have the average historical speeds for every day of the week and hour of the day. We know the location of the TMCs, the number of lanes that are on them and on the bridge itself. And then, as I mentioned, the hour of day and day of week, mostly used to assign the historical speeds for that particular TMC segment. The last input that we have comes from MBTA, and it's just the status of the lanes on the bridge. So whether they're open or closed, and if they are open, what direction of travel they are serving. And we use this for the current time period. But then, as you'll see in the demonstration here, we in the predictive part of the tool, the users can change the lane configurations and assess what the impact will be on the queue associated with that change. So just real quickly, not to get too technical, but the way that we define a queue or a TMC that is a part of a queue is we compare the observed speed, a ratio of the observed speed versus the free flow speed. When that becomes 0.6 or smaller, we say that's congested and it's part of a queue. And we do that for each TMC, so then we can build up consecutive TMCs or adjacent TMCs and get an overall general max queue length that we're seeing. In our predictive model, we try to predict the conditions at 5-minute intervals all the way up to 30. So 5, 10, 15, all the way up to 30 minutes from the current time, we predict what we think the queuing conditions will be. And the way that we did this was using an AI model, machine learning, called XGBoost, which stands for Extreme Gradient Boost. Brief overview of kind of to visualize how the methodology works. It's basically a model that builds decision trees. So it has these splits and different branches to try to improve the accuracy of the model and reduce the error that's in it. And then what it's doing, though, is it's also checking to make sure that the structure of the decision tree is not too complex. So there is a penalty that's assessed to the model performance when we have too many branches of the decision tree. So before we wanted to implement our model into the tool, we wanted to sort of do a sanity check or an evaluation of how well the model was performing. And so, as you might expect, there's a couple of different general conditions that can occur. So if T is the current time, then T plus 30, these are the 4 potential evolutions of congestion at the bridge. So it can be uncongested at the current time, and then it can become congested in 30 minutes in the future. It can be congested at the current time, uncongested in the future. And then the other 2, which are much easier to predict, intend to actually dominate the data set, is when it's uncongested, it remains uncongested, or if it's congested, it remains congested. So we built our model using just the raw data that we have, and this orange matrix that you're seeing was our initial results. And the way to interpret this chart is it's basically showing the percent of conditions that are accurately being predicted. So you'll see here, this top row, 0 stands for uncongested. And then we have falsely congested. So these sum up to 100. And basically what it's telling us is that we were able to predict of all of the uncongested events, we accurately predicted about 67%. And 32, when it was actually uncongested, our model is predicting it to become congested. Same thing for the bottom. False congestion is when we think it's going to be uncongested, but it actually is. And that was 88%. And then when it actually was congested. So the performance of the model, we want to increase these 2 cells, the uncongested and congested, and drive these percentages, both false congested and false uncongested, down. What we realized was because the transition from congested to uncongested and uncongested to congested were somewhat rare events, we had to resample the data so that we had better representation of those types of events in our input data to the model. After doing that, we have pretty significant improvement in the results. So we jumped from 67% to 88% in terms of predicting uncongested conditions. We drove down the false congestion from 33 down to about 14, or false uncongested, went from 88 down to 28, and then we accurately predicted congestion around 72% of the time. So we were, somewhat satisfied with this. There's certainly still some room for improvement, which we're going to be talking about in the slide on next steps. But we felt that this was a good starting point for us to launch the tool and provide these estimations in a user-friendly interface. So as I mentioned on the tool itself, there's 2 general views. The first one is for real-time monitoring, and the second is for prediction. I'll start by walking through the real-time. So there's different layers, that can be turned on and off. So you can look events, if there's crashes, disabled vehicles, work zones, those kind of things. There's traffic sensors, dynamic message signs, the actual visualization of the queues, the probe data itself, and weather data. And then we can jump around to different parts that we're monitoring. So that right now we're looking at the bridge itself and what the conditions are. So in the first column here, you can see the lane configuration. We have 2 eastbound lanes and 2 westbound lanes, with lane 4 being closed at the moment. The next part of the interface gives the measurements of the volume at the abutments. So both eastbound and westbound, how many vehicles per hour are we monitoring? And this updates, I think, every couple of minutes to show the updated information. We also have information on the queues, if there are queues, how long it is, and what the travel time at the end of the queue is to get to the bridge itself. We do that for both directions, a summary of the events that might be impacting the performance in the travel times at the bridge. Then we also have information on the weather at the bridge, temperature, if there's some type of precipitation, and wind speed is obviously an important one for bridge applications. But there are other sensors that we can also monitor. So anywhere you're seeing these kind of black road segment icons with different lanes is where we're getting lane-specific speeds and volumes. And right now we've focused on this one, the westbound movement at the east abutment of the Bay Bridge. So we have the lane configuration, and in this case they had 3 lanes going eastbound. We can look at the volume on each individual lane, and then you'll see a dot and an arrow. So a dot was the last 5 minutes vehicles per hour, and then the end of the arrow is the current. So this information gives some insights on whether in the recent history of the queue, is it growing or is it receding, right? So in this case, it's growing on each of the cases. The next column here is the travel time to the bridge. If it's gray like this, it's been holding steady, but other lanes are seeing changes that are increasing. We do the same thing for average speed. In this case, since the queues are growing, you might expect the speeds to also be going down a little bit. Then we finally provide some information on the recent history of the queue length at this location. So the queue length, the travel time, and then this plot shows the queue length over time, going back 2.5 hours to show how it's been evolving. I'll click on another sensor, this one here. You can see that there's just one of the lanes that look yellow. So when I click on that, it shows me the conditions. So here, there was 3 westbound lanes, and we're starting to sense some light congestion building in lane number 1. Same information as on the last slide. So again, it allows the MDTA to be proactive. When they see congestion building, they might be able to intervene and do something about it before the queues get to be too long. But since we do have a queue that's in the eastbound direction, we can go ahead and start looking at the predictive component of our tool. And you can do that by clicking on this button that says there's a queue that is growing in the eastbound direction. So we'll click on that, and it takes us to a new interface that shows us the queuing information. So right now, we're looking at the current conditions. So again, the lane configurations, 30 minutes in the past, what the queue length looked like. So the blue lines are the head of the queue, and then the light blue tails are segments that had congestion or were in queue. They were below 60% of the free flow speed. And then we also are showing, if this was assessed at 9 a.m., that's the history, and then looking forward is where the predictive models come in. And right now we're just displaying the predicted head of the queue, which you can see up here. So we're, in the future, the head of the queue is expected to move a little bit and then come back down. But if the user wants more information on how long the queue is from those heads of congestion, they can do that by clicking on this button. And then they get some additional information. So there's 2 general categories of our prediction, one where we think there's a possible queue, and one where we're almost certain that queue is going to reach that length. So the lighter purple is, there's possibility, and where you see the dark purple, that's where we think there's almost certainly going to be a queue that's developing in the future. We do that for both lanes, or for both directions of travel. after seeing this, an operator might want to, start thinking about like doing these what if scenarios if they were able to reverse a lane or open a lane that's closed. So let's go through that example where, lane 4 is currently closed and they want to change it to being open and serving the eastbound direction. So they can hit this drop down and select open. And you can see that the tool itself updated. So now we have an additional lane that's serving eastbound, and it has updated our queuing information. So now we're using these red dotted lines for the head of the queue and the shades of red for certainty of a queue, and a possible queue is like this lighter pink color that you're seeing. And you can turn any of these layers off. Right now we're showing the current conditions prediction versus the prediction where we change lane 4 to being open and serving the eastbound direction. So it's pretty flexible, allows the operators to see very specific information about how we're predicting the evolution of congestion at the bridge. So to conclude my presentation and give a summary of what we worked on and accomplished in this project is we developed this XG boost model that extracts some general pattern of congestion for short-term congestions and looking at mostly at speeds and volumes from the sensors and vehicle probe data. We recognized that the transition from congestion to uncongestion is, and vice versa, is somewhat rare. So we implemented a strategy to resample the data so it weighted those observations more and was able to truly pick up the patterns of that transition period. And we saw the pretty vast improvements in the model accuracy after doing that. As I mentioned, the current framework is mostly based on vehicle probe data as well as the sensors for the volume. So if there's probe data and sensor data, we could translate this same application to anywhere where we have sufficient data to do it. We're also working with MDTA currently to get some additional data, more sensors to count volumes, not just at the abutments of the bridge, but further up and downstream so that we can have an understanding of the additional influx of volume that might be approaching the bridge. We think that this is going to significantly improve our queue prediction algorithm. I'll talk about that on the next step slide here. So as I mentioned, we're already kind of in phase 2, and it's mostly scoping out what it would take to enhance the current tool. The main technical part that we're doing is that we're going to be looking at recently installed Bluetooth and volume sensors. So the Bluetooth sensors give us individual device travel times that can nicely supplement the vehicle probe data, and the volume sensors further out away from the bridge. And we're expecting that these new inputs into our model will improve the model accuracy, but it will also give us the ability to extend the prediction horizon. So right now we're predicting at 5-minute intervals up to 30 minutes. We think that we'll be able to extend that out. It's hard to say exactly how much out. That's an ongoing investigation, but we think at least 1 hour, perhaps more, which we give MDTA more information and time to make transitions on the lane configuration at the bridge. We're also working on creating some new interfaces as there is some desire to look at the historical analysis. How well did our prediction model do compared to what actually happened? So we're developing a separate tool for that and other enhancements to the general visualization that you saw on the screen today. I'll mention one other project that might be of interest to IBTTA. We're working on some emergency response and prediction of secondary crashes in queues. And we're pursuing adding labels for crashes that happen on or near bridges and tunnels. So we're working on integrating that and hopefully into tools like this. So as I mentioned earlier, I kind of just scratched the surface on some of the technical methodology and description of the data that we use. If you're interested in more details, I encourage you to read a paper that me and my colleague Sarah Zahedin wrote for TRB back in 2023. Has some details, and if there's further questions, of course, you can reach out to me. My contact information is on my next slide. I'd also like to mention and thank MDTA for their support and funding for this project.
Mark,
that completes my presentation. Here's my contact information if there's any follow-up questions. Thank you again for the opportunity to present.
Thank you, Mark. I appreciate it, and a very insightful information. I want to thank the Cat Lab for the collaboration and work that has happened here, and also point out, Mark, if I may, the importance of the prediction horizon, and also get increasing that from that 30 to an hour, or whatever that may be, based on sensors, as well as that footprint, because that extends both east and westbound prior to the abutment. And the further we can get that expansion of that footprint, the better we can anticipate and prepare for that traffic heading our way.
Yeah, certainly. I agree with that.
Marge, any questions?
No questions for me. I just wanted to do a special thank you for our speakers and for sharing that knowledge and forward-thinking perspective. Really appreciate it.
Our pleasure.
Thank you. Thank you, Marge. Mark, again, thank you for your time, your vision, and presentation. Really appreciate it. Again, I want to thank Marge, and I want to thank the presenters. Very well done. Please stay tuned, as this pre-recorded session will be available May 21st. And any follow-up questions or comments can be submitted to Marge or myself by email, and we'll provide a copy, or let me just go ahead and say that now. Marge, you want to provide your email address just briefly, and then I can send mine?
Yeah, of course. My email is marge.rangel@transcore.com. Happy to answer any questions.
And mine is RJARAMILLO at mdta.state.mdt.md.us. I really appreciate it. Marge, anything in closing?
On behalf of the AI Strike team, we appreciate your participation, and we look forward to continuing this important dialogue.
Thank you, Marge. I've truly enjoyed our session today. Hope you have as well. Thank you for joining us. And as always, stay safe. Thanks.
You too. Thank you.
Thank you.
Thank you.